Finding the inverse of a matrix to solve a 2x2 system of linear equations. Let's solve this system. In order to find the inverse of a matrix, of a square matrix, we're going to use the Gauss-Jordan technique. And the way we do that is we're going to first set up a 2x4 augmented matrix. That augmented matrix is going to look like this: -3, -4, 3, 5, and we're going to augment it with the identity matrix 1, 0, 0, 1, the 2x2 identity matrix. Now our goal is to row reduce this so that, let's say you have a matrix A and you have the identity here. The goal is to row reduce this until we actually get the identity on the left hand side of the augmented matrix, and then we get a matrix B over here. In fact, if this matrix B exists, we in fact will rename it and call it the inverse of A. So that is what we call the Gauss-Jordan technique to find an inverse. Why don't we begin? So let's do -1/3 times row 1, which is row equivalent to 1 4/3 -1/3 and 0. Row 2 doesn't change. Now we're going to pivot from row 1. We're going to do -3 row 1, add it to row 2. This is now row equivalent to, row 1 doesn't change, so I just recopy that. Row 2 does change. We get a 0, and we got -4 plus 5, which is a 1. And then we got a +1 plus a 0, so that's +1 here. And then we got another 1 here. We're almost done. We just need to do -4/3 times row 2 and add it to row 1. We're going to store in row 1, so that means row 2 does not change. So I'm just going to recopy that. And row 1 does change. This is a 1. This is a 0. -4/3 plus a -1/3 is -5/3. And then we have -4/3. So there's our matrix B on the right-hand side. This looks like our matrix B. In fact, this is going to be the inverse of A. Why don't we rename that? We now have the inverse of A is equal to bracket -5/3, -4/3, and then 1, 1. Now you might be wondering what A is. A is bracket -3, -4, 3, 5, right? We're going to take this original equation here, and we're going to translate this. This looks like matrix A, -3, -4, 3, 5, multiply it by another matrix, a 2x1 matrix called bracket XY in a column position. This is now equal to 15, and negative 12 in the column position. Now we're ready to multiply by the inverse of A. What happens when you multiply by the inverse of A? Beauty happens. I'm sorry, I didn't copy the inverse of A. I meant to write the inverse of A. We're going to multiply, we're going to balance this equation by multiplying on the left side by the inverse of A here, and then on this side by the inverse of A here. The order matters. We need to have the inverse of A on the left. So let me explicitly write this out. We're ready to write the inverse of A. There it is. And we simply multiply that by 15, negative 12 in the column position. Now, what do we get here? Right here, we get the identity matrix. That is actually going to be that. And then we have left, multiply that by xy in the column position. What else do we have? Over here, we get a 2 by 2 matrix, multiply it by a 2 by 1. So the output is going to be a 2 by 1 matrix. Let's figure out what that is. So we got negative 25 at negative 25 let's see here, plus 16, and then we got 15 minus 12. So what do we have? We have x, y in the column position is now equal to negative 9, 3 in the column position. How do we write our final answer? Our final answer is a solution set. It's a set consisting a unique ordered pair, and that unique ordered pair is negative 9, 3. So even though I'm just going to circle the answer here, more importantly is the work. What work do you want to show? You know, all these little steps and procedures are just as important.